In this video, we're going to introduce a more geometrical way of thinking about the integral, which is really the more important part of calculus that we need for this class. And so when you took calculus previously, you probably remember that integrals really were talking about the areas under curves. So I can draw some curve here. Let's say it's like a line like this. If I want to find the area under this curve between some point A and B, we consider these like these rectangles that we're adding up from here to here, like this. So you might remember this, but it didn't really mean very much, right? Because this is just like area under the curve. Who cares about the area under the curve? We want to do something real here. And so I'm going to build up a different way of thinking about calculus and then show you it actually gives you exactly the same thing you have here. And that's to say that integral calculus is just a really fancy way to add up tiny little pieces of something. So I'm going to start with the simplest example of something that you could add up the little pieces of, and then show how I can get back to this way of thinking about it. So consider some x-axis here. We have some x-axis, and we want to know what the length of a line segment is between x is equal to a and x is equal to b. So we have some line segment like this. Right. Now if we know that this distance right here is a, and this is the distance of b, then we can kind of see on some intuitive level that the length of this is going to be b minus a. We want to use the tools of calculus to do this. And so the way that we think about this is we say that for any line segment, you can break it into all these tiny, tiny little pieces you call dl for a length of a line. And then we can add all of them up over the total length of the line to find what its length is. And so symbolically what that says is that L, the total length of this, is going to be equal to the integral of dl. Right? So you're just adding up all the little pieces. And so in this case, this line segment is along the x-axis, so we say that dl is going to be equal to dx. And then we can say that this is going to be the integral of dx. And we can put in some limits of integration talking about where this starts from and where it goes to. Okay? So that says that this is going to be the integral of where it starts from to where it goes to. And when we do this integral, we end up finding that this is just going to be b minus a, exactly the way that we expected it to be. Now, the next thing that we can do, because this is a very powerful tool, it doesn't have to be used just for straight lines. We can do this with arcs of circles. Right? So imagine we have some circle here, and these have all these tiny little dl's as well. And what we can do, we can talk about the angle that this has right here and some radius of r. And here what this says is that this dl is going to be r times d theta. Now, looking at this, we could find what the total length of the arc of the circle is around the whole thing by saying that that L is going to be equal to the integral of r d theta, going from theta is equal to 0, where you're starting, the starting angle is 0, to where it ends. So this is going to be theta is equal to 2 pi, because we go all the way around the circle. Now when we do this integral, we get actually a very familiar result. This is going to be equal to 2 pi times r. So the length of this circle going around the whole way is 2 pi times r, which conventionally we call the circumference. Okay. Now, something else that we can do is we can extend this idea to more than just one dimension. So consider some box like this. And this is going to be x is equal to 0, y is equal to 0. And we can say that this is x is equal to a. This is x is equal to, or y is equal to b. Okay. So if we want to find the area of this box, we could just multiply the bottom, the base, times the height. So that's going to say that the area of this a is going to be equal to a times b. But we could also think about it in terms of these tiny little areas we'll call dA that have some height of dy and some width of dx. where we say that dA is just going to be the product of those two things. So this is going to be dx times dy. And then to find what the total area is, capital A, we just add up all the little pieces. Now, this says that this is going to be equal to the integral dx dy. And when we have a product of these two, we have a dx and a dy, we're really doing a double integral. And you might not have seen these double integrals before, but really all they are it's the product of single integrals. So you have this dx, where does x start? X starts from 0, x is equal to 0, so x is equal to a. And then where does y start? Y starts from y is equal to 0 to y is equal to b. And then again, we get the result that we would expect. This is going to be a times b. Now, to recover our familiar area under the curve way of looking at things, say that this is the line y is equal to x. We would do the same thing. So if we want to go up to some x is equal to a, and we want to find this area right here, you say that this area is going to be equal to the integral of dA, which is going to be equal to the integral dx dy. And then you have to say, well, where does y start? Y starts from 0, and it goes up to x, right? And the way you can see that is y starts from 0, y goes up to x, okay? And then x starts from 0 and it goes up to a. So this is x is equal to 0 to x is equal to a. And so if we do this first integral here, we end up seeing that this is going to be equal to the integral of x dx from x is equal to 0 to x is equal to a. And this is what you would typically use if you're computing the area under the curve with what are called Riemann sums. And those are these boxes that you have here, instead of the tiny little boxes that we have here. So we showed that these are actually the same thing. All right. So you can do plenty of other fun things here as well. You can extend this into 3 dimensions. You can find the area of a circle. So say you have a circle. Instead of finding just the length of the arc of the circle, you can find what the area of it is by calling this dA is equal to r dr d theta. You can find the volume of spheres or cylinders, the surface area of spheres and cylinders, using exactly the same ideas here. But those will be activities for class to finish. Okay, so that's going to be it for this video.